Hello, Chemistry of Earth and Space Science. This is the last video of the 2025-2026 school year, first semester for Chemistry of Earth and Space Science. And we're going to go over a really important concept in chemistry called the mole. So today we're going to try to convert between moles, mass, volume, and number of particles, being able to do a little bit of counting along the way to determine how many atoms there are, what is the mass of that. You'll see how this works. So this comes down to something called stoichiometry. Stoichiometry is the mathy part of chemistry, and we're going to use this measurement called the mole. So when you think about certain numbers, like you say a couple of things, you mean two. When you say I have a pair of those, you mean you have two. If you say you have a dozen of something, it means you have 12. And even if you're really good, you might know that if you have a grand, like say you have a grand of money, that would be 1,000. There are numbers associated with those terms. And just like that, we have a number that in chemistry we associate, and that is the mole. So the mole is a counting unit in chemistry, meaning if we have to count particles, how many atoms, how many molecules, we don't count actual atoms or molecules. We use this very dozen-like unit called the mole. Same way we know a dozen means 12, we also know that a mole is going to be our label for a certain number of atoms or particles. So it's a number, it's a counting piece. Now, to give you an idea how big a mole is, a mole, if I had 1 mole of marbles, it would cover the Earth to a depth of 50 miles deep. If I had a mole of pieces of paper, this one I thought was one of the more interesting ones. If I had a mole of pieces of paper, I had to just pile them on top of one another flat, they would go from the moon and back 80 billion times. Think about how much paper that is going to be to go back and forth 80 billion times to the moon. However, if you think about the mole, one thing that you don't think about is that if I had only 18 milliliters, that's a very small amount of water, that would contain 1 mole of water molecules. So that huge number applies to a lot of things around us because the things we're going to count in chemistry are very small. So since we deal with these very small objects, atoms, molecules, formula units, we need to have a measurement that is really huge. So we can count large numbers of these things, these atoms, molecules, particles, formula units at one time. Now, granted, you could use the mole for just about anything. Mole is just a number, just like a dozen. But we do use it in chemistry and even in some cases in physics to represent a number of things. So the mole. By definition, a mole is exactly the number of atoms that if I had pure carbon-12 and I measured out exactly 12 grams of carbon-12, I would have a mole of particles. So this is a very standardized unit. They use carbon-12 because it's very common as a marker. They use 12 grams because carbon-12 and 12, yay, that's cool. And then they were able to determine how many atoms were in that 12 grams of carbon-12. And this is the number, it's called Avogadro's number, 6.02 times 10 to the 23rd. Now, taking that not in scientific notation, and realize how big that is, let's see if my pad is going to wig out on me. It's 602, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. A mole of particles is an astronomically huge number of particles. It is big, and the reasons why it's so big and why we choose such a large number to count with is because the things we count with are very, very small. Now, the term here that says this is going to represent the number of particles in a mole. So I guess the question would be, what's a particle? So a particle can be any chemistry-related element or compound. So if I'm looking at specific atoms, an atom could be a particle. So if I had 6.02 times 10 to the 23rd atoms of lead, I would have a mole of lead. Molecules. Now, what is special about a molecule? A molecule is a covalent compound. Like carbon dioxide, water, phosphorus trichloride, they're all covalent compounds. So there we use the term of a molecule. And when we're talking about ionic compounds, then the more appropriate term that gets used when it's used properly is a formula unit, because it's a single representation of whatever the formula is. NaCl would be one Na and one Cl. So how do we use this? Well, what we have now is a conversion factor. We have a conversion factor using Avogadro's number. So if I wanted to count, say I had 0.54 moles of lead, and I wanted to find out how many lead atoms there were. I'm going to start with what's given to me, the 0.54 moles of lead. And we do indeed use the abbreviation MOL for mole. I know we just dropped one letter, but it is what it is. You get really used to just dropping that E. We'll start with what's given, 0.54 moles of lead, and then we need to do a conversion. Now, since we know 6.02 times 10 to the 23rd particles equals 1 mole, sorry about that, we can do this in conversion factors, much like we did in the last dimensional analysis piece, where they both are equal quantities and they go on different sides of the dividing line. But just like our dimensional analysis we did in the last video, we want to be able to cancel out our units. So if I were to want to cancel out moles, I'd want to use the one of these that has moles in the bottom. So I would take this particular one, plop it down there, and then do the math. So the math would be, let's see, do I have it here? Oh. So the math would be, I got 0.54. I'm surprised the answer's not there. Turn on the calculator. 0.54 times 6.02 times 10 to the 23rd. Sorry, my calculator is a cheap four-banger. Okay, 0.54 times 0.54 times 6.02 times 10 to the 23rd. And voila, I find that I have, if I had 0.54 if I had 0.54 moles of lead, I would have 3.25 times 10 to the 23rd atoms. Now, on your calculator, instead of typing in times 10 to the, you're going to use a EE button or an EXP button. As you get to this lesson in class, if you can't find your EE or EXP button on your calculator, see me. If you use one of my calculators, they all handle it differently. So please check out which one it is and make sure that you're able to get the calculator to do what you want. How about this one? If I have 7.96 times 10 to the 25th molecules of carbon dioxide, how many moles would that be? Well, again, you always start with what's given to you. In this case, it's 7.96 times 10 to the 25th molecules. I need to use my conversion factors, where now I have 6.02 times 10 to the 23rd molecules per mole. And I need to figure out which way I need to do this. Do I do it using the first one, or do I use the second one? If I use the first one, notice that my moles don't cancel. Molecules are here, moles, that's going to be wrong. So that's going to be the wrong one to use. I would use this one. I would use this particular one so that molecules will cancel. I'm left with moles. If I do the math, and again, the math here would be 7.96 times 10 to the, or EXP, 25, divided by 6, because that number's in the bottom, 6.02 times 10 to the 23rd molecules. And when I do that math, I find that I have 132 moles of carbon dioxide. Okay, one more. Suppose I have some barium sulfate, and I know I have 0.35 moles of barium sulfate. And we know barium sulfate is Ba plus 2, SO4 minus 2. Okay? We know the formula for barium sulfate. And I don't want to know how many barium sulfates I have. I want to find out how many oxygen atoms I have. So first thing I need to do is convert from moles of barium sulfate to formula units of barium sulfate. So I look for my conversion factors. I pick which one I want. In this case, I want to use the one that has the mole in the bottom. I put it in place. Now I have 0.35 moles per times 6.02 times 10 to the 23rd molecules per mole. And then I want to know how many oxygen atoms there are. In every barium sulfate, there are how many oxygens? There's 4. So what I would do is I would then look at my conversion factor that in every molecule of barium sulfate, there are 4 atoms. And again, decide which way do I want to use this. Do I want to use it the first way or the second way? Well, the first way will allow the moles to cancel. Sorry, molecules to cancel. Molecules cancel. Moles cancel. I'm left with only one unit. That's the atoms of oxygen. So I need to do the math. When I do the math, let's see if it does it for me. Yeah, I get 8.4 times 10 to the 23rd atoms of oxygen. Now, sig fig wise, you are using sig figs. This has 2 sig figs. This has 3. This is a counting number, so that's absolute. So the smallest number between 2 and 3 would be 2. My final answer needs to be in 2 sig figs. So this leads to a visual that I use called the mole diagram, and it starts a little like this. I have this mole concept, and I can go between mole and particles by using 6.02 times 10 to the 23rd particles per mole, no matter what those particles are. Okay, so we have 2 concepts that are really kind of useless because we can't count the atoms, and we can't get the moles unless we count the atoms. So another thing we've done using the periodic table, which is brilliant what happens here, is if you remember, the atomic mass on the periodic table were in the units of AMUs. And an AMU was a number that represented a mass unit for each one of those elements. So since we had like carbon is like 12.01, that means if I had 12.01 grams, I would have this AMU. But in this case, the AMU we're dealing with is the mole. So we have a way to connect mass to particles. We're going to use what's called the atomic mass. That's the numbers on the periodic table. We know what those are. Those are decimal numbers. And if we're talking about a single atom, like we were in the last one, we're talking about oxygens, we would just use the numbers straight off the periodic table. What's lithium's atomic mass? What's lead's atomic mass? Whatever we need to use. You're going to use the periodic table that I gave you, the green one, and use those numbers. So technically, if I did that, this one is from an older, more detailed periodic table, so we would get rid of this one-year periodic table. It just says 6.94 grams, or 6.94 is the atomic mass of lithium. That means 6.94 grams is equal to 1 mole. If you're talking about a compound, then you're going to have what's called a molecular mass. The mole of a compound. In order to get that mole of a compound, that mass of a mole of a compound, we're just going to add together the atomic masses. So for instance, water. Take 2 times 1.008, and then 1 times 16.00 for oxygen. And I add them together, and then I worry about rounding because that's what we have to do now. We're dealing with sig figs. That number, that as adding it to the right number of places, the 16.00 has only 2 digits past the decimal, so with the right number of sig figs, that value is 18.02. So if it's an element on the periodic table, we just take the number off the periodic table. If it's a compound, we add together the atomic masses for all the elements that are in that compound. A lot of terms mean the mass of a mole of. So atomic mass means the mass of a mole of atoms. Formula mass means the mass of a mole of formula units. Molecular mass is the mass of a mole of molecules. Old school talks molecular weight. That's the weight of a mole of molecules, the weight of a mole of atoms. They all basically say the same thing. This is the mass of a mole, the mass of a mole of something. So to simplify that, I personally use, instead of getting very, very specific with whether it's a formula weight, formula mass, or atomic mass, or molecular mass, they're just vocabulary. I just use a common term that's used as just a molar mass. Molar mass is the mass of a mole of anything. It's the mass of a mole of anything. So a mass of atoms would be the atom's atomic mass. That's the molar mass of that atom. If I have to add them up, that's the number I get is the molar mass of that compound. Molar mass, mass of a mole of whatever compound you're dealing with. So the units of molar mass are, I want to say obviously, going to be grams per mole. It is a conversion factor that goes between moles and mass. It's a way to go from, if I have moles, I can get mass. If I have mass, I can get moles. So we have another part of our diagram. Now the diagram has expanded a little bit to include mass. And for every substance we're talking about, there's going to be a different molar mass. So there's no magic number like the Avogadro's number. So let's see how we would use this. Suppose I want to know how many moles are in 19.5 grams of silicon. So as I say, always, always, always start with the given. And this is one where I'm going to say start getting in the habit of making sure your numbers have units and have labels. So this would be grams of silicon. I look in the periodic table to find out what the atomic mass of silicon is, and it's 28.09. And I have to determine which way am I going to use it. I'm going to use it on the left with moles in the bottom, or I'm going to use it on the right with grams in the bottom. Well, since I want to get rid of grams, I'm going to use the one that has grams on the bottom so that my units of grams of silicon can cancel. I do the math. I take 19.5 divided by 28.09, round it to the appropriate number of sig figs, which would be 3, and I get 0.694. 19.5 has 3 sig figs. 28.09 has 4 sig figs. The smallest number between 3 and 4 is 3, so my answer can only have 3 sig figs. Suppose I want to know what a mass of a mole of something is. So I want to know what's the mass of a mole of 1.25 moles of oxygen. So I'm going to use my molar mass for oxygen, and don't forget molar oxygen is O2. So when we go to get the molar mass off the periodic table, the molar mass of oxygen, the element, is 16.00. So we have double that, 32.00 grams per mole. We have to decide which way we're going to use that. Do we want to make sure that we can cancel out our moles of oxygen? So the conversion factor we're going to use is the one that has moles of oxygen in the denominator. So if I place this in this arrangement and my moles now cancel, I'm left with grams of oxygen, which is what I want. So I do the math, 1.25 times 32.00, and I find that I have 40.0 grams of oxygen. Now, if you typed this in your calculator, you would have gotten 40. But since this number has 3 sig figs and this number has 4, I need to make sure my answer, which the calculator gave me as simply 40, is shown as having 3 sig figs, which meant point and the 0 in the end. One more way to use the molar mass, and that's to bring both pieces together, molar mass and Avogadro's number. So, if I want to know what's the mass of, and I have the number of atoms, in this case it's 9.68 times 10 to the 23rd, 26th atoms of lead. I want to know what would the mass of those atoms be? Well, there's not a line that goes directly between these two, right? So I can't go straight from particles to mass, mass to particles. So I have to do it in 2 steps. I was given the particles, so I'm going to start here. I'm going to change my particles into moles. I'm going to change my moles into mass, and I'm going to end up getting the mass of my 9.68 times 10 to the 26th atoms of lead. So let's go. I'm going to start with my atoms of lead. You need to use a conversion factor. Now again, if I look at the conversion factors I have here, I grabbed the wrong one, sorry. Guess I did. Oh, there it is. I had this go from particles to moles, so first thing I need to use is Avogadro's number. So I'm going to go ahead and use Avogadro's number and calculate, or try to calculate, the mass of those lead. So I'm going to first use Avogadro's number, 6.02 times 10 to the 23rd, atoms per mole. I'm going to use this version of it, the one on the right, because I want my atoms to be in the bottom. And then I got to go from moles to mass. If I go back to my flow chart, got this one. Now I'm here, I'm at moles. This is where I am right now. I've got the number. If I stop right now, I'd get to have the number of moles of lead. I don't want number of moles of lead. I want to get the mass. So I need to use the molar mass of lead. So my next step is to look on the periodic table for the atomic mass of lead, which is 207.2 grams per mole, and determine which way to use it. And this time I'm going to use the first way, because I want to make sure that mole is in the bottom so that I can cancel my units. And I'm left with ultimately grams of lead. Put that into my handy dandy calculator and find that I have 333,000 grams of lead. That's an insane mass of lead. What if we want to go the other way? Suppose I want to know how many formula units are in 7.25 grams of sodium chloride. Again, looking at the flow chart, this time I have mass to start off with. And I want to end up in moles. So we're going to go from start to moles, moles to particles. 2 steps again to do this. So we're going to start with the 7.25 grams of sodium chloride, and we're going to change it into moles. Again, getting it to cancel, so we're going to use the second one, the one that has grams in the bottom. We're always looking to pick which one has the proper units in the bottom to cancel out the units you have. So we'll use this one. Then, the next step, we realized we had to use Avogadro's number to get to particles. So, if I look at the 2, like 6.02 times 10 to the 23rd particles per mole, or a mole is 6.02 times 10 to the 23rd particles, this time I want to use the first way, because the first way I have moles in the denominator, allowing the moles to cancel. At this point, moles have canceled, grams have canceled. I'm only left with formula units. Yes, I used the abbreviation FU. Formula units of sodium chloride, and then I just do my math, and I find that I have 7.47 times 10 to the 22nd formula units of sodium chloride. Sig figs, this is 3, this is 4, this is 3, so this has to have 3 sig figs. Last scenario. Sometimes, in order to measure an amount of stuff, mass is not convenient. And specifically, mass is not very convenient with gases because a lot of them are lighter than air and would not register on a balance. So, we're going to deal with gases, and because gases change volume based on the temperature and the pressure of that gas, we're going to only work with gases at STP. STP is standard temperature and pressure. In Chem 2 or ATIC, you will have adequate time to discuss how the volume would change as you change the pressure and change the temperature. But for our circumstances here in Chem 1/Chemistry of Earth and Space Science, we're only going to deal with gases at STP. Only gases that are at 0 degrees Celsius, which is pretty unreasonable, and 1 atmosphere pressure. 1 atmosphere pressure is not as bad. That's like normal pressure. Right now in our classroom, right now it's after school on Tuesday. It's probably about 18 degrees Celsius, and our pressure is always a little low. I say 0.965 atmospheres. So we're a little below, and we're a little above, a little below in pressure and a little above in the temperature. That's going to change the volume, but we're going to only work with gases as if they are at STP. Because any gas that is at STP will take up the same amount of volume, and the volume would be 22.4 decimeters cubed per mole. Well, the metric system kind of helped us out here. A decimeter cubed is actually what we now refer to as a liter. So we have a conversion factor that allows us to go between volume at STP and the mole, and that is 22.4 liters per mole. This number is absolute for everything. Avogadro's number, 22.4. As long as this is a gas and it's at STP, that number is good. If it's not a gas and it's not at STP, you can't go down that road. So let's look at a few examples, much like the other ones. Let's start by saying, what is the volume of 1.25 moles of nitrogen gas at STP? So we start with the moles of nitrogen gas. We're going to use 22.4 liters per mole. And 22.4 liters per mole, if we put the mole on the bottom, we get that the moles will cancel. And when we cancel them, we get 1.25 times 22.4. This has 3 sig figs. This has 3 sig figs. So my answer should have 3 sig figs, and it turns out to be 28.0 liters of nitrogen. Let's go the other way. Suppose I have 150 liters of butane gas. It's at STP. I want to know how many moles there are. So I have 150 liters of butane. My magic number that I get to deal with is 22.4 liters per mole. Am I going to use this the way it's written up here? Or am I going to flip it upside down? What am I going to do? Well, I want my liters to be in the bottom because that's what unit I have here. So I need to flip it upside down and make it be 22.4 liters per mole, but put the liters in the bottom so that I can cancel liters. I can be left with moles, which is what it's asked for. I'll do my math, and 150 has 3 sig figs, 22.4 has 3 sig figs, so my answer has to have 3 sig figs. And I get 6.70 moles of butane. Let's keep going crazy here. What if I want to know what the mass is of 6.89 liters of hydrogen gas? Now I'm incorporating the other part of this flow chart. I'm now going to say I know the volume. I'm going to start up here. But now I want to know the mass. Or is it the other way around? I actually forgot. Yeah, we went to mass. Okay, so we're going to start with the volume. So we start with the volume. We go back to that flow chart. The first conversion factor we're going to use to go from volume down to moles is our 22.4 liters per mole. So we look back at this example, and we have our 22.4 liters per mole, and I ask myself, do I leave it alone or flip it? We're going to flip it because we want our liters to be in the denominator of our conversion factor. So now, at this point, my liters are canceled, which is what I want, the whole thing of dimensional analysis. And then I go and I need to get the molar mass, because the next thing I need to go from moles over to moles over to mass, I now need my molar mass. So I go to my periodic table, I see that hydrogen has a mass of 1.008 grams per mole. But that's hydrogen, H, the element. Hydrogen gas is H2. So if I multiply that together times 2, I get 2.016 grams of hydrogen per mole of hydrogen. So I'm going to use that conversion factor in the right orientation to be able to make sure the moles cancel. Put it that way. Now I have the moles in the denominator to be able to cancel with the moles that were left over after the first step. And then I have the 2.16 grams. I punch it into the calculator and then ask myself how to round it. This has 3 sig figs. This has 3 sig figs. This has 4 sig figs. So my answer has to have 3 sig figs. And when I do that math, I get 0.620 grams of hydrogen. So we can, at this point, pretty much get around any place on this chart. We can start at any of these squares and end up at any of the other ones. And that's the first step in understanding how to do stoichiometry. Next step, come to ATIC, come to Advanced Topics in Chemistry, or the old term was Chemistry 2, Chem 2. Come to ATIC. One of the first units we do is stoichiometry, and we take this concept of the mole and we take it even further to be able to say, if I were to measure out exactly backwards. Sorry, get it back. Forgot I changed it over. If I were to measure out, say, 15 grams of, we'll do the biggest, sodium chloride, and 20 grams of silver nitrate, based on what we did with predicting products back in lesson 2, we know that one of our products is going to be silver chloride, and that's going to be a solid because it's insoluble. If I added 15 grams of sodium chloride to 20 grams of silver nitrate, the question would be how many grams of silver chloride could be formed. And you do that using stoichiometry. So I hope to see you guys at ATEC either next year or shortly after that. It's a great course. It's really, truly a excellent course to prepare you for a college chemistry course. Chemistry of Earth Space Science is not that deep, and if you had to take a chemistry course in college, you would be pretty lost from the beginning. So what better way to be on top of your studies, especially if you're going into the sciences, than to take advanced topics in chemistry. So I will see you in advanced topics, or see you in class tomorrow. Toodles.